Okay, good evening once again. I'm Dr. Iwara Ripo from the Department of Computer Science here at the University of Calabar. So now, the next thing we need to look at is the historical background surrounding computer technology. You see, until we are able to identify where we were in computing and calculations, we will not be able to appreciate where we are and where we are headed. Remember, our parents, our descendants, our ancestors have used stones, they've used pebbles. At that point, at some point in history, like in places like Egypt, we were told that people have clay and then they engraved numbers on those clay. They put strokes, tally system on them, they tally lines on them and cross. There are sometimes they put those things on stones. They carve stones to indicate numbers. That's all the origin of computing. But now the most identifiable origin now in the modern generation is where we start with the abacus. An abacus is also called a counting frame, as you could see on the picture from the picture on the left. The abacus looks like a window with lines, like normal rods in our windows, with bits all around it. With those strings, trained operators can be able to achieve thousands of computation. It originated with the Chinese around 3000 BC, although we've been told that there are some books that will tell you that it was developed by the Babylonians, but the Chinese history had become more pronounced. Thereafter, we can identify the slide rule. The slide rule looks like those who did intro tech, you see the micrometer screw gauge, how the micrometer screw gauge functions. The slide rule functions close to that. But the people in those times, around 1620, were able to use that to do a lot of calculations. You could see the numbers on it as they shift the dial with the number, with the line, red line on it, they're able to achieve calculations. So the slide rule was developed by a man called William Oughtred in the 1620s. He's an English. Then we look at the mechanical calculators era. During this period, we have what they call simple mathematical calculators. And the first mathematical calculator was developed by a Frenchman called Blaise Pascal. That was in 1642. His machine is called Pascaline. And the state of that machine was that it could only do addition and subtraction. Then after some time, science, there's addition and addition and addition. There's a man they call Gottfried Leibniz. He enhanced this machine to help that machine do addition, multiplication and division. So the Pascaline in an enhanced form could be able to achieve division through repeated subtraction, and it could be able to achieve multiplication through repeated addition. Then we got to the time of the Jacquard loom. The Jacquard loom was invented by a Frenchman called Joseph Marie Jacquard between 1802 and 1804. This machine was originally designed for the textile industry to be able to design patterns on clothing. That was the original arrangement of this machine, the original purpose of this machine. But because in those days, information was keyed into cards, they call punch card. The punch card looks like a conventional class admit card. So this machine could be able to do patterns on the clothing. So the Joseph Jacquard now thought it could be deployed to be able to program and make holes on punch cards that computers can read and make sense of it. That was how this Jacquard loom came into computer technology and was used as a punch card working machine. Then we get into the analytical engine. The analytical engine started as the difference engine, and it was developed by an Englishman called Charles Babbage in 1822. So it started as a model of a computer called difference engine. So that model gave Charles Babbage a guide on how to enhance it, and now develop what is called the analytical engine that has a few components that represents the storage, the processing chamber, and all that. And that is why Charles Babbage is now referred to as the father of modern computers. After the analytical engine, we have the tabulator. We have tabulator. The tabulator was developed by an American statistician. His name is Dr. Herman Hollerith. Dr. Hollerith was a statistician, and he developed the tabulator in the year 1886. So because of the efficiency of the tabulator, this machine was deployed in the 1890 census of USA. And so it reduced the time of computing the American census by about 3/4. What used to take them several years to accomplish. Now we get to the area of ENIAC. ENIAC is in history seen as the first true general purpose electronic computer. ENIAC stands for Electronic Numerical Integrator and Computer. It was invented by two men from Pennsylvania University, John Presper Eckert and John Mockley. Now, in those days, this computer was so fast. It could perform 5,000 calculations in a second. And of course, you know, if your computer now performs 5,000 calculations in a second, then you throw it away, you know that it's a useless machine because it will be too slow for your liking. But in those days, it was supersonic. It was fast for a computer to do 5,000 calculations in a second. Now computers work in nanoseconds. That's 10 raised to power 9 minus 9. That's the way computers of the speed compared to now what we are seeing here. These computers were very bulky. ENIAC was very bulky. And so it could occupy a massive building up to 30 feet by 50 feet. One computer could fill such a big mansion. And because of their size, they consume a lot of power, up to over 150 kilowatts per hour of electricity. So because of this, they generated a lot of heat, and so ENIAC had to be water cooled for it to be able to function. Now we get into this fundamental concept called the stored program concept. It's a fundamental and famous concept that everybody who does any history on computing has to know the stored program concept. The stored program concept was proposed by a Harvard mathematician and chemical engineer. His name is John von Neumann in 1945. What are the key components of this stored program concept? John von Neumann postulated that computing devices were not limited to the functions of representing and storing data in the computer's electronic circuitry, in the computer's components. That computers could do more apart from just storing and representing data within itself. That is stated that instructions for manipulating data could be coded and placed inside the computer itself. And that's what we see today. Now we are able to store, you have your computer has the software, which is the instructions already installed in the computer. And so you just load it and it's able to manipulate your data without you having to put diskette, having to put, because these things are now inside the computer. So that was what he was saying, that instructions for manipulating this data could be coded and placed inside the computer itself. He also stated that calculations could be carried out without human intervention. Before now, what used to happen is that after every operation, in fact, the course of the operation, wires are reset, switches are reset, wires are done, reversed completely, and there's a lot of work before one single operation could be done. John von Neumann said that this could be done, computers have capacity to do that without humans going to rewire the system. Based on this, the stored program concept has remained a fundamental component of all computers, and it helps to distinguish computers from all other electronic devices. Now, all computer architectures, the hardware and the execution capabilities are all built around the John von Neumann's stored program concept. Now we look at generations of computers. Now, computers have been grouped according to the technologies that are identifiable by science. The generation of a computer is a stage in technological advancement of computers. So there are a lot of details that you may not find here, but the truth is that these are the clear identifiable technologies we can tie to different stages of computer development. So when we talk about generations of computers, we are simply talking about the different stages of computer technological development that are identifiable as computers advance from one stage to another. And the first generation of computers happened around 1946, covered around 1946 up to 1956. And the core technology at the time was the vacuum tubes, which looks like the conventional old electric bulbs we used. So now, one fundamental problem of vacuum tubes being used to develop computers was the fact that, you know, these are bulbs, they are big, number one. So thousands of them in one computer will make the computer so large. And that was why ENIAC, you could see the picture of ENIAC. You could see the picture of ENIAC here. ENIAC could occupy a complete building because ENIAC run on vacuum tubes. Again, just as our electrical bulbs are unreliable, vacuum tubes, they generated a lot of it and so died off so quickly and made computers of the first generation so unreliable. That push for the advancement that led into the second generation of computers, which covered between 1957 and 1964. And this second generation of computers was based on transistors. Transistors look like those components in our old transistor radios. Of course, some of you were not born then. The old transistor radios was made of transistors all over. So the transistors were like 1/18 of the size of a vacuum tube, if not more. So the advent of the second generation of computers that are based on transistors reduced the size of computers drastically smaller as compared to the first generation of computers. But science was not done. There was still push to make computers more miniaturized, smaller than the first generation computers, smaller than the second generation computers. And that led to the advent of the third generation computers, which covered between the time 1965 to 1970. And they were based on a technology called integrated circuits. An integrated circuit is a chip that is made up of thousands of transistors packed into one silicon chip. So this defined the computers of the third generation. And as such, because if you have thousands of transistors packed into a small chip, you could not imagine how reduced computers could have become in the third generation. And it was during the third generation that software programming languages were now becoming more popular. Individuals could be able to use the computer, but at this stage, individuals could not afford, most individuals could not afford computers because computers were still relatively big and a bit quite expensive. Now, the greatest leap in computer technology was the advent of the microprocessor. A microprocessor is a single chip made up of millions of transistors packed into one silicon chip, and that chip is able to carry out the full-fledged capability of a full-fledged computer. So the biggest advent in computer technology was the era of the microprocessor. So this was the time now we started having laptops, microcomputers, because during the third generation we had things like mini computers, but at the fourth generation laptops came in, microcomputers came in, because computers now could be made far smaller. And they could still do far more than what the previous generation of computers could do. Now we get to the 5th generation computer, which is the last generation, which is where we are now. The 5th generation of computers started in the 1982, and we are still in the 5th generation of computers. And they were based on the concept of artificial intelligence. Parallel computing. Artificial intelligence tries to make computers to try to do something like what we can equate to what reasoning. Computers to try to reason by themselves and act a bit independently. But don't forget, it is programs that are running them. Parallel computing, where you now have computers with multiple processors and are able to do several things at the same time. Then you have also the 5th generation of computers was also based on artificial neural networks. The artificial neural networks is a computing arrangement in which computers are so networked like the human neuron in the body. So there's a net of computers. Several millions of computers are communicating and communicating seamlessly so that information could be tracked and easily moved all around. So that's neural network. So the key goal of the 5th generation computers was to develop devices that will respond to natural language. So people can make input in natural language, and then they will be capable of, the computers will be capable of learning, and they organize themselves. So that's what you find in robotics. Like the picture you find on the right is an example of artificial intelligence implemented in a robot to do things. Now we look at the second to the last of our discussion today, which is types of computers. And it's instructive to note at this point that computers can be classified in either of 2 ways. You can classify computers based on their mode of operation. That's why we say types of computers. You can also categorize computers based on their size and power of functionality. Those categorizations, we call them classes of computers. So for this section, we'll be looking at the types of computers. Like I said, it's a kind of classification according to the modes of operation of computers, and there are 3 modes of operation of computers. So we categorize computers in terms of types into 3. You have analog computers, you have digital computers, and you also have hybrid computers. An analog computer is used to monitor processes in a manufacturing industry, and it is used in measuring signals in engineering. So it's most measuring devices, voltmeter and all that are examples of analog computers. A computer using a measuring scheme is usually making an analogy between 2 conditions. Example, a speedometer is used to make an analogy between the rotation of the shaft of the tire, as well as the speed with which that vehicle is traveling. That is why you read the speed on your speedometer. That's an example of an analog computer. It's a computer, but it's an analog computer. Other examples include an analog fuel pump, what we find in the filling stations, in electrical systems, the voltmeter, like I said, and then in power grid supply, you find analog computers fully functional in those settings. Now we look at digital computers. A digital computer naturally processes data that is represented in the form of discrete values. Discrete values are numbers that are non-fractional, such as 0, 1, 2, to infinity, but they are non-functional. They're fractional. There's no fraction. So these ordered numbers are called discrete values. So digital computers process data that is represented in this form, and it operates on this data step by step. Digital computers convert all their inputs, all the numbers, all the alphabets, all the alphanumeric, that is alphabets and numbers, and they convert all those characters in binary coded form. That's the only language the computer understands. Remember that the major language of the computer is called binary coded language, which is zeros and ones, representing presence of voltage or absence of voltage. So the digital computers will convert everything you put in the computer into binary coded form. That's the only one that the computer recognizes. Example of digital computers are all the computers you see around, all the ones you have, your laptop, your pantops, and all that are examples of digital computers. Now we look at hybrid computers. A hybrid computer is a specialized kind of computer that has the combined features for digital computers and analog computers. A hybrid computer can be obtained or can be achieved by the direct interconnection of a digital computer with an analog computer in a very specialized way. Now, since there's an interconnection between the analog and digital computer, remember the analog computers, they work with signals. Digital computers work with codes. So how does a hybrid computer function to deliver on its mandate? Well, a hybrid computer has a device that helps it to convert analog signals into digital codes for the computer to punch and calculate. That device is called a digitizer. When those processes are completed in forms of codes, the results is now available in numbers and all that. For example, if it's in an oil rig system, all that computation will mean nothing. Let's say in a blast furnace, like in the element petrochemical, that computation could mean that there should be less pressure on the fire that is burning the crude, or there should be more pressure. But it will not translate to anything except those commands that have been generated by the digital component are translated into electronic signals that will compel the blast furnace to act according to these instructions. Then the device that helps to translate these digital codes into analog signals is called a converter. So an example of an analog computer is found on the right side of the screen. Now let's look finally at the classes of computers. I've said earlier that when we talk about categorization of computers, talking about the types of computer, which is categorization according to the modes of operation. Now, classification based on classes. Here we're talking about a categorization of computers according to their sizes and their speeds of operation. So under this arrangement, we can categorize computers according to their sizes and speed of operation based on 5 categories. You have the embedded computers, you have microcomputers, you have mini computers, you have mainframe computers, and then you have supercomputers. Let's look at the embedded computers. Well, these are computers that are hosted inside the bodies of other consumer products. For example, your microwave oven, your modern television, they all have embedded computers. And that is why these devices are able to operate with some level of automation. So computers that are embedded, you can't operate these embedded computers directly because they are hidden inside the bodies of other devices. So these computers are called embedded computers. So they are embedded inside other devices. And they help to automate some of the operations of their host products. For example, you can set up your microwave oven to do a lot of things, to warm food and stop at a particular time, and then to time it depending if you bring food from the freezer and it's completely frozen. There's a component called defrost. You use it, it will defreeze what you brought. So it has different levels of automation because it has embedded computers inside it. Some of the products with embedded computers include digital cameras, microwave oven, compact disc sets, cars, digital watches, and a host of other devices. Now we look at the second class of computers, and each class has a slightly faster speed and bigger size. We are now looking at microcomputers. Remember that when we say that the biggest advent of computer technology was during the 4th generation computers, which was the advent of the microprocessor. A microcomputer is a computer whose main processing capability is placed inside a microprocessor. And that is how the name was derived, microcomputer. So the smallest and is the smallest standalone digital computer, and it has the slowest speed compared to other higher versions, and the smallest memory capacity. A microcomputer uses a microprocessor as the main processing component. So everything that happens in a microcomputer happens in the processor, which is one silicon chip. Now it's further divided. The microcomputer is further divided into what we call the palm tops. Most of you have palm tops, most of you have laptops, most of you have desktops. And now laptops are now even further divided and miniaturized further to be smaller. Now you have netbooks. Netbooks are now doing the work that microcomputers, big microcomputers used to do. Netbooks are now used to do all kinds of things. They are so powerful that what used to happen even with big microcomputers are now being done with netbooks. Some of your tablets can do what a full-fledged computer can do. That's to show you the further miniaturization of microcomputers. Now the next class of computers is called the mini computer. The mini computers are basically multi-user systems. It means that the mini computer can give computer access to multiple users. Mini computers can give access to 200 to 300 users at the same time by connecting these computer terminals to it. Let's take example of a banking system, a banking hall. Every bank branch you get to, you always see computers, tellers. A teller is somebody who attends to you at the bank, helps you to cash your money, helps you to deposit your money. These are called bank tellers. Each of the bank tellers, you know that they sit before a computer. And you find computers all over the hall, used by different people. This, and of course, you can give a check to somebody to be cashing while you're even paying him money through a different teller in the same banking hall. That should inform you that these computers are all connected to one major computer somewhere. That major computer is called a server, and that server is always a mini computer. So all these computers speak to one database, and that database is hosted in a mini computer. So in the banking hall as a whole, there's a mini computer somewhere that's providing information across the entire banking hall. So that's why they say it's a multi-user computer. It's not a computer that you sit down as an individual and be operating it. The capacity is more than one individual. You'll be rendering the computer nearly useless. The sizes of the mini computers now lie between the microcomputer and the next higher computer, which is the mainframe computer. Now, the mini computers are practically disappearing because of the further miniaturization and enhancement of microcomputers. Now, some of the roles that mini computers were handling, microcomputers have been so enhanced that they can do those things. A microcomputer can be used as a server. So the enhancement of microcomputers have practically rendered mini computers useless. Now let's look at the next class of computers, which are called mainframe computers. Well, mainframe computers are the power horses and the cornerstone of modern day large-scale data processing operations. So let's use the banking hall example to describe this. Remember that every major bank in Nigeria have thousands of branches across the country, hundreds of branches across the country, sometimes across Africa. Now you can go to any of these African countries where those banks exist and cash money. While you come to Nigeria, you see cash money from the same bank. That should tell you that the information, because the physical cash is not moving, is the information that is traveling left and right. The information is stored in one computer at the headquarters of that bank. The computer that stores all those other information where the mini computers are talking to it, like every branch has a mini computer. Now speaking to the mainframe computer. So the mainframe computer can accommodate thousands of computers. So it's like the workhorse of the large-scale data processing. So all banks have at their headquarters at least one mainframe computer where all the branches speak to. That is why you can stay in Calabar and somebody can pay money into your account from Lagos and can draw it here because the database resides in the headquarters of that bank at their mainframe computer. Because of their sensitivity, mainframe computers must work 24 hours, non-stop. So their downtime can be very costly. That's why you see banks, they struggle a whole lot to be sure that their downtime is near zero because they can't afford to be off operations. So the mainframe computers must run around the clock, and then they must have a retinue of operators, maintenance personnel, programmers, and data entry clerks all working to keep the computers functional and doing what they're supposed to do, because the computers must process millions of requests at any given time. Just as you're using your computer to access your bank, to see your balance, and people across the world could be using, wherever the branch of that bank is, could be using the same mainframe to access their banking information. Now we look finally at the last class of computers, which is called supercomputers. Supercomputers are the fastest and the most expensive computers in human existence. In fact, they are beyond the purchase of individuals. They are so fast that they are best used for scientific and engineering operations, where heavy mathematical calculations must be completed, such as weather forecast, launching of rockets into orbit, and major scientific operations that the mainframe computers do not have speed to cater for. Supercomputers do that. So they are highly expensive. They are used in the defense industry, like in the American Defense Department, and highly sensitive departments use supercomputers to do that. And because of this, their incredible method of operation, incredible speed of processing, they are commonly referred to as monsters. So a supercomputer is also called a monster. So practically, this brings us to the end of chapter 1 of the course Introduction to Computers. So all the details, you can find them in the textbook GSS 211. But basically, this is a summary, although most of these things were treated before we treated these things with you before the COVID lockdown. But this is practically a summary of your chapter 1 of the Introduction to Computer, which is actually the introduction to the course itself. So thank you very much for listening.